Hello, my name is Matthew Jones from the University of Lorraine. Welcome to this introductory lesson about mastering network traffic filtering with IP tables. IP tables stands as a powerful command line tool essential for configuring and managing filtering rules on the Linux kernel firewall. Developed by NetFilter project and distributed at the GNU GPL license, IP tables play a pivotal role in securing and governing network traffic. Through the specification of rules and chains, IP tables determine how packets are treated, offering capabilities in packet filtering, network address translation, and packet mangling. This versatile tool finds its utility in understanding and analyzing filtering rules that apply to network traffic. By allowing users to define criteria such as IP address, port numbers, protocol, and packet states, IP tables empowers administrators to implement precise and effective network policies. The flexibility and granularity offered by IP tables make it an indispensable component of safeguarding Linux-based systems and networks. In IP tables, the organization revolves around tables, chains, and rules, providing a hierarchical and structured approach to configuring and managing packet filtering in Linux systems. Tables are organizational structures that group chains based on their functions. Tables are fundamental to categorizing rules and determining the type of processing that should be applied to the network packet. Each table contains predefined or user-defined chains. Chains are sequences of rules that define how the packet should be processed. They act as a set of instructions for the firewall, determining the fate of the packet that traverses the networking stack. Rules are directives that define how packets should be processed within a chain. Each rule consists of a criteria that the packets must meet and an associated action to be taken when the criteria are met. The most common actions include accept, drop, and modify. Here are some of the tables and chains to use within the IP tables ecosystem. The filter table contains an input chain, forward chain, and output chain. The NAT table consists of a pre-routing chain, forward chain, and post-routing chain. The mangle table consists of pre-routing, input, forward, output, and post-routing chain. We will see where within the network stack these tables fit into in later sessions. Now let's talk about the IP tables flow process. Incoming packets traverse through the pre-routing chain of the mangle and NAT tables. Destination address network address translation occurs at the NAT table's pre-routing chain. Routing decisions are made on the destination IP address after the pre-routing. After routing, the packet enters the input chain of the mangle and filter tables. For local processing, if the IP address matches that of the local system, the packet goes through the input chain of the filter table. Rules in the input chain determine whether to accept, drop, or reject the packet. For forwarding, if the IP table is not destined for the local system, it enters the forward chain in the filter table. Forwarding decisions are made based on the routing rules present within the RTM. Final processing checks and modifications such as the TTL are performed in the post-routing chain. The packet leaves the system through the post-routing. Now let's explore the actions associated with rules, particularly focusing on the filter table and the NAT table. In the filter table, we have three fundamental actions across different chains. First, there's the accept, where the network packet is gracefully allowed to proceed. On the other hand, there's drop, that takes a more direct approach by discarding the packet without notifying the sender. Lastly, there's reject, that also drops the packet but ensures the sender is informed of the decision. Moving on to the NAT table, we encounter two powerful actions. DNAT, or destination NAT, that allows us to rewrite the destination IP address of the packet. This can be handy in scenarios where we need to redirect traffic to a different destination. Conversely, we have SNAT or source NAT that empowers us to rewrite the source IP address of a packet, providing flexibility in managing how our network appears to the external world. Now let's look at some of the usage and key parameters. One common task is listing the rules associated with a particular chain in a given table. This is accomplished with the command iptables-l, chain name -t, table name --line numbers, providing a clear overview of the rules along with their line numbers. Now, when it comes to manipulating the rules, iptables offers a set of powerful commands. To add to a specific rule to a specific chain in a given table, we use iptables-a, chain name -t, table name -j, target. This allows us to dynamically shape the behavior of our firewall by appending rules as needed. In a situation where precise control is required, we can insert a rule at a specific position within the chain using iptables-i for insert, chain name -t, table name, rule number, -j, and target. This flexibility enables us to fine-tune our rule set to match the specific requirements. Lastly, removing a rule is straightforward with iptables-D, chain name -t, table name, rule number. This ensures that our rule set remains manageable and reflects the current needs of the network security. The rule number can be obtained by a first command which highlights all the line numbers for each given rule. In essence, these commands grant us the ability to inspect, adapt, and refine the rules governing our firewall. Now let's look at a series of examples on adding, removing, and viewing rules using iptables. In the image below, we can see the list of rules in the table filter. This is done by using the list command as shown in the image. The --line -numbers is used to display the line numbers for each rule, thereby establishing the exact position of the rule within a chain. Next, let's add two rules, specifically rules to allow HTTP and HTTPS traffic coming from any network. We can do this using the append command. In the image below, we add two new rules. One to allow all TCP traffic coming to port 80 and one to allow all TCP traffic coming to port 443. These are the specific ports used for HTTP and HTTPS traffic. We then list all the current rules that exist within the filter table. As you can see, the rules for HTTP and HTTPS traffic have been appended to the end of the chain input. Now, we want to allow SSH connections from a specific network subnet. To do this, we can use the -s network address /mask to specify which network to allow that specific rule to match on. In the example below, we match on all traffic coming from 10.0.0.0/24 network that have the transport protocol as TCP and have a destination port as 22. Now, let's try remove some rules. To remove rules, we can use the information we gathered from the list function previously, specifically the line number. In the previous list, let's delete all the rules associated to FTP service. To do this, we use the -d command. Here, we use the -d input 3 -t filter command twice. The reason being is that once rule number 3 is deleted, rule number 4 becomes essentially rule number 3. The updated IP table filter table is listed below in the image. Now let's look at some advanced IP table configurations. One powerful capability of IP tables is the ability to configure port forwarding between two interfaces. This is basically achieved by using the first command listed in the slide. Here, the -J DNAT or destination NAT is used to specify the destination IP address and port. Here, we dynamically redirect traffic from one interface to the other, allowing for precise control over how data is forwarded. Additionally, IT table also enables us to configure a simple network address translation between two interfaces, a common scenario in routers. To do this, use the second command listed in the slide with -out interface and -J masquerade. This ensures that the outgoing packets have their source address rewritten simultaneously. Also, using the third command on the slide, we can ensure that the NATed packets also have filtering between interfaces. Sticking to the same topic, let's look at two examples. In this example, we configure IP tables to perform port forwarding. Specifically, we add two rules to forward all traffic coming from port 80 and port 443 to the host 192.168.130.10. By applying both these rules, all traffic received on the interface on port 80 and port 443 will be forwarded to the specified host. In this example, we configure a simple NAT operation with masquerading. Here we add two rules. The first rule is added to the NAT table and appended to the post routing chain. This enables all traffic received to be forwarded to each 0 interface with the source IP address masqueraded or replaced. Furthermore, we add a second rule to the filter table to the forward chain, enabling us to accept all traffic coming from each 0. Thank you for your attention. With this, we finish the explanation about mastering network traffic filtering with IP tables in the context of cybersecurity.